Hello everyone. In this video we're going to be introducing another algorithm called the shortest path algorithm. This is going to be somewhat similar to our minimum spanning tree work. We're again trying to find something to minimize. Our goal here is given two vertices. What is the shortest way I can walk across a weighted graph to get between them? We've seen something like this before with the shortest path for a non-weighted graph. We actually were able to solve that with breadth first search. That won't work here because breadth first search had no notion of a weight on the edges. So how are we going to solve that? So our goal is find a path from, let's actually write from and not frau, from U to V that has minimum total distance. So the aggregate of each of the edges chosen along the path. What do I mean by that? Let's say we wanted to have a path from 1 to 13. Here's an example of a path from 1 to 13. We go from 7 to 4 to 8 to 6. Sorry, we go from 1 to 2 to 3 to 4 to 5 to 13. So the cost of that path, cost of path P, we'll call that P, is 7 plus 4 plus 8 plus 6 plus 4 plus 8 plus 6 plus 4. So the total cost is 11 plus 8 is 19 plus 10 is 29. So that is a path with a cost. Is that the path with the minimum cost, though? It's not obvious that it is. So let's try and check out some other paths and see if we can do better. Let's try another simple, obvious looking one. Maybe go along the bottom. If we go this path, that path, that path, that path, that path. The green path here, P prime, the cost of that is 8 plus 4 plus 5 plus 4 plus 6. That gives us 12, plus 9 is 21, plus 6 is 27. Is that the best path? It's really not obvious that it is or isn't. Let's try another one. Let's try, we'll do this one in blue. Start out the same, because this one seemed like a good start. But instead here, we're going to go from 11 up till 9, and then over to 10, and then up this way. If we look, we made an improvement about this rhombus-shaped structure there, where the paths diverge. We went from 5 and 4 in the costs to 3 and 5. So we've reduced the cost by 1. So the cost of, let's call that path Q. The cost of Q is going to be to take the previous cost and subtract 1, so it's 26. Is that the minimum? It turns out it is, but verifying that seems actually rather difficult. So, what can we do to try and verify this? Maybe if we sat there and thought about it for a while, we say, well, let's try and think about something else. What if I knew the minimum path to each of these vertices, the ones I blocked in purple? If I knew the minimum cost to all of those, every single one, then I could just choose the minimum of those costs plus the new edge. So suppose we somehow figured out those costs, everything adjacent to the end node, we could then use that to find out the best place, or the best way to get to the final node. So, what do I mean by that? Imagine that there was a better path to get to 10 than the one we just took in blue. So if there was a better path, if there was a better path to 10, then the minimum path, or the shortest path, to 13 would be, or would use, that better path. So if to one of the nodes incident to, for one of the nodes adjacent to the endpoint, if there was a better path, we would choose that better path and then take the last edge over to the last node. We will write this down later as a theorem, but this is a useful idea. In fact, this idea of generalizing the problem and looking at all of the nodes adjacent, and then all of their adjacent nodes, and then all of their adjacent nodes, and working our way backwards is actually going to be a bit helpful. So, what we're going to do actually is be somewhat greedy. We're going to find from the starting node, I'll box it in orange, from here, what is the shortest path I could take to any node? The shortest path I could take to any node would be this path up here, because there's only two choices I could make. I could either go to node 2 or to node 8. There is no other option. Now, looking at what I have so far, what is the shortest path from 1 to any node? Well, I can go to 8 with a cost of 8. I can go to 8 with a cost of 9. I can go to 6 with a cost of 15, and 13 with a and 3 with a cost of 11. The shortest one would be to go to node 8. We will then keep doing this. What is the next best choice I could make? And if we stare at this for a while, we can find out that it's going to be this one up here with a cost of 11. 7 plus 4 is better than 15, is better than 15, is better than 12. So now the nodes I can possibly go to are 4, 6, and 11. The best way to get to 4 would be up here, and there would be a cost of 19. That's not very good. On the bottom, that's a cost of 12, and here we have a cost of 15. So now we would go down this way. And now let's look at what the best ones are. We have a cost of 15, a cost of 19, a cost of 15, and a cost of 14 this way. So now 6 is connected. So now we have, let's maybe shade these in a different highlighter color to really emphasize this. Let's do this weird sort of pale blue. That's not a good highlighter color. Let's do this pale purple. We've added these nodes to what we will call a shortest path tree, similar to our minimum spanning tree. So what nodes can we find? We could find node 4. We could find it in a couple of ways, though. We could find it with a cost of 11 plus 8, which is 19. A cost of 15 plus 4, which is 19. We could find node 7 by doing 15 plus 7. That's 22. We could find node 9 by doing 15 plus 4 is 19. We could find node 9 by doing 12 plus 3. That is 15. That looks like my best choice. So now the next node we add is node 9. Now what nodes can I add? If I go along the bottom here, I can add 12 with a cost of 17. I still have all of the same stuff up top. I could add node 10 with a cost of 20. So 17 appears to be the winner. Now let's check what else we have. We have node 7 here with a cost of 15 plus 7, which is 22. We have node 4 up here, which has a cost of 11 plus 8. That's a cost of 19. And we have node 10, which has a cost of 20. So 19 appears to be the winner. Now, if we remember the numbers we just said, we had 19 and then 20 was the next best. And all of these new nodes up here have a cost greater than that. Oops, undo. Better color. And now if we look up top at those nodes, we have a cost of 21 to get to 7 and a cost of 22 to get to 7 this way. So the next best choice we could make would be to go down to 7. And then we add it. Sorry, forgot to shade in 2 of these. We added that, and we added that. We have 2 nodes left to add. The best ways to get there would be either via 7 or via 10. 10 at a cost of 20. So this is 26 to go up this way. This had a cost of 21, so it's a cost of 29 to go that way. This had a cost of 19 plus 6, that's 25. 25 is the best. So we go there. Now we have 1 node left to add, and the best way to get there is the shortest path we found before. I didn't store the right information there to make that convenient, which we will see how we can do that later. But we're doing this somewhat in the way we're doing the minimum spanning tree. Look at all of the nodes we haven't added, all of the white nodes, and for each of them, find the best way to get there. And we're finding the best way by comparing it to the tree we've already built in some way. And we'll see a better implementation of this later. So, if we wanted to find the shortest path from 1 to 13, the best way to do it actually is to find the shortest path from 1 to any possible node, and then use that to find the shortest path to a particular node. So step 1 is build what's called a shortest path tree. Step 2 is to use that shortest path tree to determine the shortest path to a particular node. If all I did care about was the shortest path from 1 to 13, the second I found node 13 via this process and knew the shortest path there, then I would then be able to stop the algorithm. So if I had added 13 before the very last node, then I would have been able to terminate the algorithm ahead of time. That unfortunately wasn't the case, though. So this is the algorithm we're going to discuss. This is going to be called Dijkstra's algorithm. It is another example of a greedy algorithm, and we will see that when we look at the code of the algorithm. But what we're doing is always choosing the next closest place to go. Whether or not that's correct or not, we will see in a video. But for now, we're just going to take it on faith that it is correct. And that's all we're going to do for introducing the algorithm. We will talk in other videos about correctness and about the algorithm itself and its implementations.